Welcome to the lecture of scalable data science. Today we will talk a little more about locality sensitive hashing. In particular, we will sort of see how to build hash tables out of the locality sensitive hash functions that we have been discussing, right. But to start with, just to review, this was the problem of finding near neighbors, and we are trying to build data structures that answer queries like what are the k nearest neighbors and give me the list of candidate nearest neighbors within a particular distance maybe. Okay. And the tool that we are focused on are these kinds of hash functions, right. What we have said is that suppose we have a similarity function, right, and a similarity function is something that takes any two objects, right, and intuitively gives us a similarity between these two, right. And mathematically we can say that it satisfies a few simple properties like s of x y equal to 1 if and only if x equal to y, and as s of x y equal to s of y x. So, given such a similarity measure, we are now asking the question of, does there exist some hash family H such that we can choose, let us say uniformly for now, let us say uniformly from at random from this hash family, and so that the probability over the choice of H, the probability that H of x equal to H of y, the probability that any two x and y collide, right, that H puts them in the same bucket, is equal to the similarity of x and y, exactly equal to the similarity. Okay. So, and we are wondering whether such hash families even exist. So, we have seen at least for two such families, for instance the angle based similarity as well as the Hamming similarity. At least for two such similarities, we have seen that we have proven the existence of such hash families. In this lecture, we will investigate a little bit more about some other similarity measures, and then we see how to actually use these families, such hash families. So, the first distance or similarity measure that we want to consider is Jaccard distance, right. If you remember, if you do not remember what Jaccard distance was, it was this very simple idea that if you have two sets A and B, right, the Jaccard distance between them is defined as as this quantity, right, J of A B, this is the Jaccard similarity, not the Jaccard distance. Jaccard similarity between A and B is defined as A intersection B divided by A union B, the cardinality of these two, right. So, and we want, and this is a similarity measure, right. So, now we are asking that does there exist a hash family, right, that is locality sensitive for this similarity measure, right. And here is a solution, right, and the solution was initially suggested by Broder in a beautiful paper, and then subsequently worked upon by Broder and Mitzenmacher. So, the family consider all random permutations of the universe U, right. So, there are, if the universe size is n, there are n factorial random permutations, pick any one of them at random. Pick any one of them uniformly at random, right. So, my hash family is the set of all random permutations of the universe U, and I get to pick any one of them uniformly at random, and now I calculate the probability, right, and now how do I map a set, right. I can say that I map each element of the set according to this random permutation, right, and we will see an example right now. I map each element of the set according to this random permutation and take the minimum of these values, right. So, I take the minimum of the elements of the set, the values of h of x, okay. So, you can imagine, you can sort of, so without loss of generality, we can say that the universe consisted of the numbers from 1 to n, right. So, then taking the minimum is actually pretty well defined and nice. So, we consider a random permutation of 1 to n, and then take over all elements in the set, you calculate the minimum of h of x. So, it is often easier to visualize this if we think of the collection of, if you have multiple sets, if you think of the collection of sets as a 0 1 matrix, and that is what we will do. Let's see an example, right. So, in this example what we have done is that the rows here are the elements, these are the elements. So, A B C D E F G, this is the universe. So, the universe consists of the set from A to G. Okay. Now, there are 4 sets. Set 1 consists of the elements A, B, F and G. Set 2 consists of the elements C, D, E. Set 3 consists of A, F and G. Set 4 consists of B, C, D and E. Okay. So, I have put in 1s in those places and zeros everywhere else. Okay. Now, consider a random permutation of this set, of this universe. So, what is a random permutation? We just randomly permuted the elements, right, which means that let us say that A was still put in the first place, C is put in the second place, G is put in the third place and so on, right. So, now once we randomly permute, right, let us randomly order the rows of this matrix according to this random permutation, right. So, if you are worried about thinking about the matrix, think about only one column, right, think about the column S 1. So, now S 1 had the elements A, B, F and G, right. So, previously A was in position, A was row number 1, B was row number 2 and then came F and then came G. Now, according to this permutation, I still have to write A as row number 1, but then I have to write G according to this order, then I have to write F, then I have to write B, right. So, then if I choose what is the min over x belongs to S1 h of x, right. So, think of h of x as giving me the instead of random permutation, you could also think of h of x as giving the number, right, in the sense that it says that A goes to position 1, C goes to position 2, G goes to position 3 and so on, G goes to position 3, F goes to position 4, B goes to position, this is really the permutation. It's essentially for every slot it tells you which is the item that should go to the slot, right. So, then if you calculate this min of this quantity, that what is the min over x belong to S1 h of x, effectively it sort of, in terms of this matrix visualization, it turns out that you need to look at the first row for the column S1, you need to look at the first row that contains a 1, right, because the rows are ordered in terms of the hx values, the current hx values, right, and the first row that contains a 1 and the row that contains a 1 are the only rows that belong to the rows that contain a 1 for the column S1 are the only elements that belong to this set, right. So, therefore, in this visualization, doing this operation would mean that you reorder the rows according to the random permutation, and then for every column you choose the first row that contains 1 according to this reordering. So, here for S1 it turns out to be A, which is the number 1. So, S1 gets mapped to 1. So, h of S1 is 1. Similarly, what is h of S2? So, S2 contains elements C, D and E, right. So, in this order, so if you look at the column of S2, it still contains elements C, D and E, of course, because the sets do not change, but now C is placed first, right. So, h of S2 is really now C, right. S4, so S4 might be more interesting. So, in S4, right, now although it contains B, right, according to this ordering C comes earlier than B. So, h of S4 is now also is due to C, which is also equal to 2, right. So, then the sketches for these elements, so then the sketches for the corresponding sets is the sketch for S1 is 1, sketch for S2 is 2, sketch for S3 is 1, sketch for S4 is 1, 2, right. So, according to this ordering, these are the sketch values. Seems pretty weird, but we will sort of see what it really is in a few minutes. So, here is another permutation. Here is another permutation, right. That suppose now the permutation, now again it is the same set of sets, but now the permutation is D first, then B, then A, then C, F, G and E. Okay. So, D is mapped to 1, B is mapped to 2, A is mapped to 3 and so on. So, what are the sketches of S1, S2, S3 according to this permutation? Again you now reorder the rows according to this permutation and then go to the column of S1. You go to the column of S1, you see according to this order which is the first row that contains a 1 in this column, okay, and that is the row number 2 corresponding to B. So, the sketch of S1 is 2. Similarly, the sketch of S2, right, is now corresponding to D, it is 1. Sketch of S3 corresponding to A, it is 1. Sketch of S4 corresponding to D, it is again 1. So, the sketch of the four things S1, S2, S3, S4 is 2, 1, 3, 1. Right, sketch of S1 is 2, sketch of S, I have written down the corresponding sketches in the columns. So, this example was taken from the lecture slides of A.V. Maria Terzi. So, the big question now, right, why is this locality sensitive hashing? Okay. So, as in what we are looking to argue is that why is this statement true? That if I sample a hash function, i.e. a random permutation, right, and then I define the hash of S to be according to this min thing, then why is the probability that h of S equals h of t exactly equal to the Jaccard similarity between S and t, right. And again it is a very simple, but very clever argument, right. So, think of the two columns S and T, think of the two columns S and T. Okay. So, the first, so look at the different rows. Okay. So, rows that are 0 in both S and T, they do not really need to be considered at all, right, because they will never be the I mean h of S will not be one of these rows and h of t will not be one of these rows. So, I might as well throw these rows out of the system. So, the first row, right, whether one of the two has a 1, that is whether either S, the column S has a 1 or the column T has a 1 or maybe both, right, but at least one of the two has a 1, right, belongs to S union T, right, because that particular element by definition belongs to S union T, right. And we have an equality only if that row, only if the first row, right, according to this permutation contains 1 in both positions S and T, right. But that means that the first row actually belongs to S intersection T, right. What that means is that we can rewrite the statement that h of S is h of t only is the same as the event h of S is equal to h of t is the event that among all the rows in S union T, right, the one that comes up first according to the permutation that I have sampled is a row that actually belongs to S intersection T. It cannot be anything else. This is clear. So, what we are saying is that among all the rows that belong to S union T, the row that comes up first, right, is a row that belongs to S intersection T. Only in this event will h of S equal h of t. And so, the probability of these two events are same, right, but because the rows are being, but because this is a sample uniformly at random, but because this is a uniform random permutation, the probability of any one of them, I mean there are S intersection T rows, right. So, the probability of any one of them being the first, I mean S intersection T rows in the intersection, the probability of any one of them being the first among S union T rows is exactly S intersection T divided by S union T, right. If you have 3 rows in S intersection T and 10 rows in S union T, in a random permutation, probability that one of 3, right, is the first among one of these 10 is exactly 3 upon 10. Okay. So, So that basically proves that Jaccard similarity has a locality sensitive hash family. But again, as an aside, let us talk a little bit about how to choose random permutations, right. So as per the calculations that we have been doing before, random permutation, there are n factorial random permutations. So, if we want to choose a random permutation, the algorithm needs at least log of n factorial bits, which is like n log n bits, right. It needs that much storage in order to save the random keep the random permutation in storage. This is quite a lot, right. In theory, what you need to define are a family of just like we have been defining small families of k wise independent or k universal hash functions. Here also you need to define families of mean wise independent permutations, right, approximately mean wise independent permutations. So, in practice what we typically do is as follows: you take standard hash functions. For instance, you take MD5, you take murmur3 and any fast reasonable hash function, right, and then you hash all the values into, let us say, hexadecimal numbers or some strings, and then you just sort them, right. That is all we do, right. So, there are some studies that show that there is some bias that comes into this, but it is not very it is not been sort of shown to affect real life applications very seriously, but this is an area of active research, I must sort of admit that it is not a very satisfying solutions if we use hash families about which we do not really prove anything. I mean, there are other hash families, and if you are interested in this, you should look at the work of Mikkel Thorup in order to look at how to sort of create hash families that are fast, that are implementable in a fast manner, as well as have provable properties. So, then comes the question that okay, we have been pretty lucky or maybe we have been pretty choosy in terms of talking about the distance functions, talking about similarity functions, right. So, there is a entire wide zoo of similarities and distances that are used in scientific literature. There is actually a book called Encyclopedia of Distances, right. Will there be, or Encyclopedia of Similarities also, right, for instance. So, will there be an LSH for each one of them, right? Does every similarity measure, basically every similarity function that satisfies those simple properties have a corresponding LSH, right. So, let us just call a similarity measure to be LSHable if there exists an LSH for it, okay, just a shorthand for that. And here is a very simple theorem, right. We say that a similarity, remember we are talking about similarity measures, right. We say that a similarity measure is LSHable. This implies that 1 minus s is actually a metric. What is a metric? Metric satisfies these three properties. So, that d of x y is 0 implies that x equal to y, but this is already satisfied by any 1 minus s, because s satisfies the corresponding property. Symmetry is also satisfied by any 1 minus s. The big question is this, right, that does 1 minus s satisfy triangle inequality. And what we say, what this very simple theorem says is that if s is LSHable, then 1 minus s must satisfy triangle inequality. Or to take it the other way around, if 1 minus s does not satisfy, if you can show that 1 minus s does not satisfy triangle inequality, then you can show that this similarity measure is not LSHable according to the definition of LSH that we have given, right. Let us try to prove this very small, very cute theorem, okay. So, here is what we will do. Suppose there is a hash family H, right, any hash family, okay, and so pick a hash function H belongs to H and define the event. So, we are defining a 0 1 indicator random variable. So, the random variable takes in three things, delta H, A and B, two sets A and B, and the random variable is 1, right, if H of A is not equal to H of B, and it is 0 else. So, it is a 0 1 random variable, right. So, now it is also easy to see that 1 minus SAB is the probability of H delta HAB, right, by definition. I mean, because okay, that suppose, let us do a contradiction, that suppose we say that that S is LSHable. Well, not really by contradiction, we are assuming that S is LSHable, and that is what we go with, So, S is LSHable and therefore, this is true. Okay. So, let us proceed. But now, what you can say is that this particular statement is true, that the random variables, the 0 1 random variables delta H A B, delta H B C and delta H A C, they must satisfy this property, and it is easy to see why, right, because the left hand side, right, says that A is, so H of A not equal to H of B or H of B not equal to H of C, and if one of these events happen, then it must happen, right. So, okay, or let's argue the other way around, that supposing H of A is not equal to H of C, right, then it must be the case that either H of A not equal to H of B or H of A or H of B not equal to H of C, right, which means that if this right hand side, if this delta H A C is equal to 1, it must be that one of the left hand side random variables also becomes 1, which means that this triangle inequality is satisfied by these random variables. But if that is the case, right, but if that is the case, then just plugging in the then just plugging in the expectations, plugging in the fact that this is also equal to the expectation of H delta H A B, right. We take the expectation of the left hand side and the right hand side, and then we immediately get that 1 minus S has to be a metric. Okay. So, let us look at some examples of non-LSHable similarities, right. So, here is a, we will define a similarity and then we will look at the corresponding distance function to be 1 minus DAB, to be 1 minus SAB. So, a sort of popular one is Sorensen dice. It is SAB is 2 A intersection B divided by cardinality of A plus cardinality of B. So, if you take A equal to just the element A, B equal to just the element B, C equal to just the element AB, you can easily see that SAB is 0 and SBC and SAC are both 2/3, right. What that means is that, if you take the corresponding distance functions, the distance of AB would be 1, distance of BC equal to distance of AC would be equal to 1/3, right. So, this does not obey triangular inequality. Okay. Similarly, another popular one is the overlap metric, which says that you take A intersection B divided by minimum of the cardinality of A and cardinality of B. Right. Even here, for the same example, you see that SAB equal to 0, SAC equal to 1 equal to SBC, and therefore, you can calculate the corresponding distance values. Distance of AB is 1, distance of AC equal to distance of BC equal to 0, right. So, therefore, it does not obey triangle inequality, right. And so, that simple thing gives you a proof that there is no, that these similarity measures are not LSHable, right. So, now we have seen both examples. We have seen examples of similarity measures, we have seen a bunch of important similarity measures, and we have seen LSH constructions for this, and we have seen we have seen similarity measures that are not LSHable. However, we need to go a little further, right. We need to relax, as we will soon see, that for at least one more important distance function, specifically the set of L1, L2 metrics, we need to relax the definition of LSH that we have, right. And here is what we will do, right. And now we are shifting from defining LSH in terms of similarity measures to defining it in terms of distance measures, because we saw that being a distance metric is actually more important, right, because all similarity measures do not have LSH, but I mean there is it does need the property of being a distance function at least, although that is not a sufficient condition, that is a necessary condition. So, we say that a family H is small r big R capital P small p capital P LSH if, right, if let us say if two, let us say this is x, if two points x and y are distance less than equal to r, small r, then the probability of collision according to H is at least p for some p. If 2 points x and y are at least capital R distance apart, then the probability of collision is less than capital P. Okay. So, what are we saying now? We are strictly relaxing the definition that we had, because previously we said that no, it monotonically decays with the probability of collision monotonically decays with 1 minus distance, or monotonically decays with similarity, right. So, now we are saying that no, we do not really sort of bother so much. For points we have 2 radius, right. I mean these radius will be fixed based on fixed later based on applications. We have a smaller radius, we have a bigger radius is probably a constant fraction of the smaller radius. If the points are closer than this bigger than this smaller radius, then we say we want to have a high probability of collision. If the points are farther apart from the bigger radius, we want to have a low probability of collision, just these two, that is it. Okay. So, what can we do with this? So, first of all, why did we need this? Okay. So, it is easy to see that this is a generalization of the previous definition, right. For instance, if you take the Jaccard similarity, right, and if you take the and the corresponding distance, if you say that the Jaccard distance is less than or equal to r, it is easy to do this line of arguments that says that the Jaccard, in that case the Jaccard similarity is at least 1 minus r, and the previous hash function, that is meanwise hash function that we were doing, is the probability of collision according to that is at least 1 minus r. If the Jaccard distance is bigger than capital R, right, then the probability of collision is at most 1 minus capital R. So, then our previous LSH meanwise independent permutations, they gave us a small r capital R 1 minus small r 1 minus capital R LSH. Okay. That was fairly easy to see. Okay. So, here is one for which we did not, we do not know of any LSH according to the previous stronger definition, the Jaccard similarity definition. There is an LSH according to this slightly weaker definition. Okay. So, and this is the standard Euclidean norm, right. So, suppose we have the x and y, we measure the Euclidean norm as a sum square of the distance, the square root of that. So, how do I construct an LSH for that? So, we have 3 components. First, we take a unit vector u, right. Then we chunk, we sort of have a w, and then we sort of build chunks on these intervals in the unit vector of size w, right. We also have a b that is decided uniformly between 0 and w. So, think of this as a jitter in the, that sort of decides where the 0 of this chunk of each chunk is. It sort of adds a random shift, right. So, then the h of a particular the h is now a function of u and b. These are the 2 random choices, right. And now h of x is defined as you take the dot product of u x, you add the shift, and then you sort of bucket it by w. So, in some sense what you are trying to do is that you are trying to see that, okay, if I do a random projection, right, of this x onto this line u, if I do a random projection on y onto this line u, what is the idea of the bucket that it falls into, right. So, the bucketing is of size w and it is a randomly shifted bucket. So, you want to see what is the idea of this bucket that it falls into. Okay. So, this is what we will try to do, and this is the hash, this is the hash value for any x. So, why is this an LSH? So, I will not go through the exact proof of this, and these numbers that I have written down is more or less approximate, but basically here is the idea that suppose you know that x and y are very similar. Suppose you know that x and y are less than w by 2 apart, right. Then there is a very high chance, because then the distance their distance in their in after projection is also less than w by 2. So, the only way they could sort of fall in different partitions is because of the random shift, and the probability of that is fairly small, right. You can bound the probability that if the random shift is less than, let us say if b is less than 1/3, right, then they will not really be shift, then they will fall in the same bucket in some sense. So, this is fine. Okay. So, now suppose x and y are very far apart, the bigger than 4w, right. So, now if they are falling in the same bucket, which means that if they did fall in the same bucket, which means that the picture is something like this, that they are very far apart, but maybe the random plane is somewhere here, which means that their projection in this projected line, the distance is not very big. But that means that the direction, that means something about the direction of the projection line. That means that the direction of the projection line, right, has a particular angle with the direction of the line x y, right. In fact, it sort of lies in a particular cone around the line x y, right, and you can bound the probability of that, right. And so, we can make statements that say that okay, that if the distance is less than w by 2, then the probability of collision is at least 1/3. If the distance is less than, let us say 4w, then the probability of collision is at most 1/3, which means that we have a hash function that is w by 2, 4w, 1/3, 1/4 LSH according to our previous definition, right. Okay. So, now what do we do with these functions? Okay. So, now here is the problem that we want to solve. Suppose we want to solve an RC near neighbor problem. What does that mean? What that means is that given a query point q and a target distance r, I want to return all points that are within this target distance, right, and I do not want you to return any point that is CR away from the target distance, right. I do not want you to return points outside of this CR, this is a strict no, but I want you to return everything inside the smaller ball, and for things in between I do not care, you might return them. Okay. So, why is this important subroutine? This is an important subroutine because suppose you do this, that suppose you have a subroutine to do this, then at least theoretically what you could do as follows. You could sort of take powers of r to be 1 plus epsilon times the minimum distance, r to be start with r to be the radius of the entire data set and decrease it in powers of 1 plus epsilon, right. So, you get logarithmic number of possible values of r, build a data structure for each of them, right. Now, given a particular query, search in each of these data structures, right, and you can say that by searching each of these data structures, you can actually find out the nearest neighbor to the query q, right, because the nearest neighbor will have some distance r, right, and at that right data structure you will stop, right, and then you will be able to answer this nearest neighbor question if you have the subroutine. Okay. But then how are we actually using these hash functions for this, right? Because here is the problem. The problem is that look, if you plot the distance versus the collision probability of the hash functions, let us take the Jaccard distance, right? It sort of goes down very smoothly, right? It's like 1 minus d, right? So, we do not want that. What we want is a picture something like this, that we are given r, we are given CR. What I want is that the collision probability should be very high if the distance is less than r, the collision probability should be very low if the distance is bigger than CR, and in here I do not care, it can be anything, just that I want this to be high and I want this to be low, right. So, how do I achieve that? And this is the next big idea in LSH, which is by helping you do this amplification in probabilities. Okay. So, here are the two operations that we will do. That first we will do what is known as ANDing. What is an ANDing? Instead of a single hash bit, see this is one of the original hash functions that we were constructing. Instead of taking one of them, take k of them and then build a tuple out of them. let us say these are 0 1, then build a tuple out of them, a k tuple, right. If these are numbers, build a tuple out of them. Right. And now my new hash function is this tuple, new hash value is this tuple. Okay. So, now what is the probability that h of x equal to h of y? Of course, it is the because we also choose them independently, these k functions independently. So, then it is a product of these probabilities. So, then if all of them are identically distributed, so it is a probability that one of them collides to the power k, because because this probability is a function of the distance between x and y, nothing else. But see, what might happen is that while see everything, because we are doing everything to the power k, all the probabilities fall down, right. But then if 2 points are close, even that probability is falling down, So, now I want to raise that, right, because I want to say, we might have achieved this, part, because we have pulled all the probabilities down, but now I also want to achieve this part, the fact that if the distance is small, right, the probability of collision is very high. Okay. Then the next thing that we do is ORing, and this is actually fairly simple. This says that okay, you have one such h, now build multiple such hash tables, right, one for each of the h's. So, create some capital L number of h's, each of them. So, each such capital H1 is again built out of a tuple, right, but now build capital L such big hash tables now, right. Now, when we search for a query, right, you go to each of the hash tables and then you search for each of them, right. You basically then take the union of these hash buckets, right, and then you search for a near neighbor in the union, right. So, then this union is a union over the L tables. You are looking at the candidates in all of them, putting them together, and then trying to find out the near neighbor. Okay. So, there are two steps. One is a ANDing operation in some sense, in which you are building a composite hash function using a tuple of smaller hash functions, and the other is ORing operation in which you are sort of creating multiple tables and you are putting them together, and you use all the tables when you are trying to look for a query. Okay. So, here is a simple example, for instance, right, because previously remember we saw two we had these sets S1, S2, S3, S4, we had one random permutation H1, and that had this sketch. For S1 it had 1, for S2 it had 2, S3 and this should be S4 really. For S4 it had this, and similarly we had H2 which had this sketch. So, now this would be capital H1. So, capital H1 of S1 would be equal to the tuple 1, 2. Then capital H1 of S2 would be the tuple 2, 1, right, and then we would build a table out of this. The next table would be capital H2, which is built out of yet another two independent hash functions S3 and H4. So, S1 is mapped to this tuple, S4 is mapped to this tuple, and so on. Okay. So, that is what we will do. So, why is this good? And this is the intuition that suppose you are trying to write down the probability for given q and any y, you are trying to write down the probability that hq equal to hy, right, and we know that for the basic hash function this probability depends as the distance between q and y, 1 minus distance between q and y, right. Then the probability of finding y as one of the candidates in this is this expression, and let us analyze this. So, this expression is a probability that in one of the in one of the capital H of capital H of q equal to capital H of y, right. This is the probability that it is 1 minus d to the k. So, then 1 minus that is a probability that capital H of q is not equal to capital H of y. That raised to the power L is a probability that capital H of q that q and y fall in different buckets in all the L hash tables, right. So, 1 minus that is the probability that at least in one of the capital H, one of the capital L hash tables, Q and Y have been placed in the same bucket. Okay. So, there are 3 steps here, and you have to carefully go over that. And it turns out very interestingly that if you plot this function, it looks something like the sigmoid curve more or less, right, which is that you can choose the values of k and L depending on these radius, on the radius r and cr, such that it is high in this part and it is low in this part, and it kind of goes down smoothly here, right. And that is what we will do. So, just to bring formally, write down formally that if we have a base hash family that is R, CR, let us say P, Q, LSH, right, then for any y such that Q minus y is less than R, the probability of y as a candidate in this after looking at the L capital L hash tables is 1 minus p to the k to the this raised to the power L, because this is the probability that it is a candidate in one of the hash tables, is not a candidate in one of the hash tables, that raised to the power L is that none of the hash tables return it as a candidate. 1 minus that is the probability of getting it as a candidate in at least one of the hash tables, right. And similarly, if Q minus Z is bigger than CR. So, now we are looking at Q, we are looking at one Y that is close and one Z that is far, right. Similarly, then you can say that okay, the probability of that Z appearing as a candidate in any fixed hash table is less than Q to the k by this definition. Therefore, the expected number of such Z is L times Q to the k. So, now what do I want? I want to choose the values of k and capital L. I want to choose it so that this probability is high and this expectation is small, right, because this expectation is what is driving my query time. Making this expectation small will reduce my query time, making this probability high will increase the probability that I actually find the near neighbor y, right. So, let us see if we can choose these values, right. It turns out, and this you should really convince yourself by plugging in these values, that it is possible, I mean that the important quantity is this ratio rho between the log p and the log q, right. And if you set L by n to the rho, and it is important to note that rho is less than 1. Rho is less than 1 because p is p is smaller than p is larger than q. P is log 1 by p is less than log 1 by q. So, 1 by p is less than q, we need that, which means that p is larger than q. Okay. So, and you need to choose L to be n to the rho, and you need to choose k to be log n by log 1 by q. And if you plug in these values, you can make this probability to be at least 1 by e, 1 minus 1 by e, and you can make this to be less than equal to n to the power rho, right. This might not seem very exciting to you because it is still n to the power something, but see it is a big breakthrough, right, because now this is the query time is now n to the rho, and we can make, and which is sublinear, and it was not at all clear if we could make it sublinear ever, right. And so, the number of, and so the space required is n to the power 1 plus rho, right, because you have n to the rho hash tables, each of them needs n space, okay, and the query time is n to the rho, right. So, and it also turns out that if you analyze the actual the basic hash functions of Hamming, angle, etc., you can, if you want a C approximate near neighbor, you can set rho to be 1 by C. I mean it is enough for rho to be 1 by C, right, which mean what does that mean? That we can get a 2 approximate near neighbor if C equal to 2, right. We can get a 2 approximate near neighbor in time that is query time that is square root of n and space that is n to the power 1 plus half, 1.5, right. So, by sort of not blowing up the space too much, we are still able to substantially reduce the query time from n to square root n. Okay. So, just to summarize, in order to design, I mean this is all nice in theory, but in practice the theoretical parameter guarantees are only a guidance. what you really need to search for, I mean in practice, is you need to really search over the parameter space to find a good operating point, the values of k and l. There are some ways of guiding this search by looking at some data statistics, and we will see that in next class. So just summarizing overall, the LSH is actually a very powerful tool for nearest neighbor search problems. It has it's a very active area of research as well as practice. It's used a lot in practice. The basic theme is to trade off space with query time, right? And it's one big kind of open question is that it's really practical for medium to large data sets, because you're blowing up space, right? So you can't really deal with billions of data sets, and sort of doing it in distributed manner is also kind of an open question. It's practical for medium to large data sets with fairly large number of dimensions, but it's not clear how to make it work for very sparse, very high dimensional data sets, right? So there are some there are some thoughts that people have sort of, there are some active lines of research here, and if you're interested, you should look at some of these references. One of them is the book that we have pointed to in the syllabus, Modern Massive Datasets by Rajaraman, Leskovic and Ullman, and the other is this excellent survey, as well as a number of other very recent papers by Alex Andoni in the page that he maintains on LSH at MIT. And that's it for today. So, thank you.